Hey everyone. So this is part two, the fun part. We're now going to use the functions that we've defined last time over here to run a sequence of analyses in OpenSees. And the sequence that I'm specifically thinking of is I think it's going to be fun to run a whole bunch of analyses while varying the area and try and find which one of those analyses gives us results that are close to some criteria that we set. So let's say we're doing a gravity analysis. So we'll get rid of this lateral load. And let's say the criteria that we want is we want the deflection over here to be 0.01 meters. So we're in our sequence of areas that we try, we want to find the one that's closest, that gives us the deflection that's closest to this deflection. And let's say that we're interested in areas between 1 inches squared and 20 inches squared. So for each of A1 and A2, we'll need to try every possible permutation. So for example, A1 and then A2 from 1 to 20, and then A1 will equal 2, and then we'll do A2 will equal 1 to 20, and we'll keep incrementing like that. And we want to find, of all of those combinations, which is going to give us the deflection that's closest to this amount. All right, so let's get into things. Let's just create a new section for our code, and we'll call this area optimization. Okay, analysis. Oh my god, insert just terrible. There we go. Okay, so let's start by defining our upper bound and lower bound. So we'll say lower bound equals 1 times inches squared. Upper bound is equal to 20. All right, and because we're going to be running all of these different analyses, we need to first define some variables in our code that are going to help us do that. So we're going to need to store the output variables, and we're also going to need to create like a sequence of these of different areas to pass to the analysis. To do this, I'm actually going to use some NumPy functions. So let's import NumPy. Import NumPy as NP. If you don't know what NumPy is, it's a Python package that's used pretty frequently in scientific computing, and it allows us to process data in a really convenient way. There's a lot of really useful functions. So the first, let's say the number of increments, we're going to go from 1 to 20, and there's going to be 20 increments, including this one. So we'll say n area equals 20. And so we need to have the grid of values. So we're going to use a NumPy command. We'll say trial areas equals np. We're going to use a linspace command. And basically what this does is it returns an array with values between this upper bound, the lower bound, the upper bound, if I can type, upper bound. And then the number of steps. So we want 20 steps. We'll pass 20 into the function. All right, so we need to have the grid of values, and then we also need a storage array, and I'll create this. We'll call it output displacements. So output displacement, and that's going to equal. We're going to initialize an array using NumPy again. So NumPy zeros, and it's going to be a 20 by 20 array because, of course, we're changing A1 between the lower and upper bound, but we're also changing A2 between the lower and upper bound. So it's going to be 20, and actually better would be if we passed in this area so it's parameterized properly. Okay, so let's just run this really quick. If we look at our variable explorer, this will make things a lot simpler. We can see the displacement array. It's just zeros right now because we defined the zeros array, the correct size, but you can see it's 20 by 20. Python starts at 0, just if you're wondering what's up. So 19 by 19, 20 by 20, we can figure it out. And then from here, we want to actually define the loop that does our analysis. So let's start defining that loop. I'm going to use the enumerate command because in addition, we want to be like, I'll just show you. So it's going to look like this: for I and A1 in enumerate trial areas. So what this is doing is the I variable is our incrementer, and we're going to use this because we need to store each displacement in our output. So we need to have access to what is our depth in the incrementation, and then A1 is the value in trial areas. So if we look as we defined, we have these values defined in meters squared from 1 inch squared to 20 inches squared, and this is going to basically, for every value in here, is going to assign A1 to the value, and then we're going to do whatever with our variables I and A1. We need another enumerate command. So this is for A1. We're going to do the same thing for A2 because we're looping through all possible areas. So for JJ A2 in enumerate, again, we can use trial areas because we're using the same. We're looking between the same bounds for both. Okay, now this is where we get to our code. So we've defined our A1, our A2, and for each of these, we're going to run a gravity analysis. So let's copy our gravity analysis, paste it here, and then at the end, so I'm actually going to go to this gravity analysis, and I'm going to remove the wipe command at the end of it because I want to be able to access the model at the end of the analysis. So let's just put the wipe outside. And before we wipe, we're going to get an output of the model once the analysis is finished. We of course could just read the recorders, but because we only want one output, and in fact, let's get rid of the recorders because we don't really care about, we don't necessarily want to write all, like, this is going to run 400 different analyses. We don't really want to have 400 different files here. We just care about the specific output that we wanted, which we defined it over here as this displacement. Actually, so yeah, let's go ahead and define that as a variable before we do anything. Let's see, target displacement, and that'll be 0.01 meters. Okay, and so we're going to check the output of our model using a command called node displacement. So there's a whole bunch of output commands. If you go to the OpenSees Wikipedia, you can see them right here, actually. We can check all of these things, but in our case, we want node displacement. And specifically, we want displacement of node 4 in the y direction, so displacement of node 4 in the y direction. this is one of the things that you would probably just have to look up. I've been using OpenSees long enough that I remember what the commands take, but for yourself, if you're using a new one of these, you'll have to look it up on the Wikipedia. And let's just, to convince ourselves that everything, that it's actually running properly, let's print this value. So if when we run, we're going to get a whole bunch, 400 different output displacements. So good, we know that's running properly. So now let's store those. I don't want to print that anymore. So let's take our output displacement variable for value I, we're going to store it. And then, so I is going to correspond to area 1, j is going to correspond to area 2. So what we're doing here is we're running all these analyses. So let's just run it. And if we look at output displacement in our variable explorer, we now have all of these. And of course, this makes sense as our areas get bigger, our displacements are getting smaller, and we kind of expect this one to be our smallest displacement. Okay, so this is great. We've actually done all the hard OpenSees stuff. The next step is going to be to parse our data and find the one that's closest to this node displacement. So this is like just a purely programming task, but luckily it's pretty easy to do with NumPy. So I'm going to subtract this displacement. Let's call this shifted output. It doesn't really matter what we call it. It's going to be a temporary variable, but so I'm going to subtract this target displacement from every displacement, and I'm also going to take the absolute value using NumPy. So we subtract the two. We want to find the one with the smallest absolute value now, because that's the one that's going to be the closest to our target displacement because of math. So I am there. How are we going to do this? We're going to use a function called mp_where. This checks all the indices in our. This checks all the values in our indices against a condition. And I'm not going to lie to you. When I was looking up this task, I just went to, oh wow, let's correct that variable name. Output, yeah. Sorry, when I was looking up this specific task of finding the minimum like indice, I just went to Stack Exchange. So this is none of my brilliance here. But yeah, just if you're looking up how to do something in programming, or if you want to know how to do something in programming, chances are someone else has had the exact same problem. So looking stuff up is definitely your friend. But yeah, so where are we going to store this? We have to do this weird kind of indice thing. So bear with me. Because the way this command returns the values is it actually returns them in arrays, and I want to get them out of the array. But this is going to be min index x, and this is the min index y. Okay, mp_where. So now if we run this file, we can see this is giving us our minimum index. Let's just confirm that these values actually make sense. Let's go to our output displacement. So we're trying to find the value that was closest to 0.01. And yeah, this seems pretty close. Okay, perfect. So these indices that we're getting make sense. We've checked it. That's great. So now we have those, we can actually return the optimal values. So let's do that. Let's say A1 optimal equals, and we just need to call the trial area and the x index, and then A2 optimal will be the y index. I feel not very good about how I've named these indices. I probably should call this A1. There we go. Okay, that's great. So if we were to run this, we would get the combination of the two areas that will give us our the desired condition up here. And then using those, we can now run our final pushover analysis with those two values. So let's set that up. Let's copy these guys. No, these guys. Let's see, A1 optimal, 2 optimal, and what are we going to call this? We'll call it optimal area analysis. Let's use an underscore. Analysis. Great. Perfect. So, yeah, let's run this guy now. Okay, so we can see what this is doing is we find the two areas that meet our criteria, and then on that final one, we're going to do a different analysis on the final optimal area. And we can see that it's run. We can see that we have, oh, oops, sorry. I always forget the wipe command. Okay, now if we look in here, we can see element forces, no displacements for our optimal analysis. And of course, we could change our condition if, say, we were interested in the one that's closest to, I don't know, 0.075. We could run like that. Then everything's just done for us super quick. Imagine having to actually use your brain and analyze this truss. No way. We just use OpenSees and we brute force everything. But jokes aside, you can see how this is, I think, an incredibly powerful principle. Had some sort of computer program that like calculated the optimal result, or you were using like a spreadsheet with like statics, this would take a lot of time. To find this target displacement, it wouldn't necessarily be the hardest thing in the world, but here this is all in one package. We're able to use OpenSees as both like the pre-analysis portion. Like you can think of this as like pre-analysis, where we're trying to figure out what final parameter to put in our analysis, and then the actual analysis. So I think this is, of course, this isn't something you could do on a bigger model. It's not necessarily practical to run 400 models of a building, but I think there are a lot of applications where being able to chain lots of analyses in a row will really allow us to save a lot of time.